Hello everyone, this is Brian or Lasan Cordova and welcome to another math class. So our topic for today is sequences and series, convergence and divergence. So what are sequences? It is a list of numbers a sub 1, a sub 2, a sub 3, and so on, written in a given order where each of a sub 1, a sub 2, a sub 3, and so on are called terms of the sequences. So a sub 1 is the first term, a sub 2 is the second term, and in general, a sub n is the nth term. The integer n is the index of a sub n, which is the nth term. So integer n indicates kung pang ilang term na yung a sub n na yun. And the most common sequences are arithmetic progression, which we have a formula for a sub n, which is equal to the first term plus n minus 1 times d, which is the common difference between the terms. And we have a geometric progression, which has a formula for a sub n, which is equal to first term, a sub 1, times the common ratio raised to n minus 1. And we have a harmonic progression. Formula for a sub n is 1 over a sub 1 r raised to n minus 1, which is reciprocal of the geometric progression. And the most famous sequence is the Fibonacci sequence, where your nth term can be solved by adding the previous two terms. So f sub n is equal to f sub n minus 1, which is the previous term, plus f sub n minus 2, the second previous term, where the initial conditions f sub o is equal to 0 and f sub 1, which is the first term, is equal to 1. So sequences are denoted by set notation, braces, and inside that we have the a sub n, which is the nth term. So the a sub n describes each of the term of the sequences and described by rules that specify the terms, such as a sub n is equal to square root of n, where its terms are square root of 1, square root of 2, square root of 3, up to square root of n, and so on, which can be shown also as a set containing square root of n, where your n is starting from 1 up to infinity. We also have b sub n, another sequence, which contain each term in the form negative 1 raised to n plus 1 times 1 over n. So as n increases, so substitute n in the formula, so we can get the sequence of b sub n is equal to 1, negative 1 half, positive 1/3, negative 1/4, up to the n term, which is denoted by b sub n, then so on. Another example, c sub n, with the formula for c sub n, or the n term, is n minus 1 over n. So we have the sequence 0, we have n is equal to 1. So we have a denominator 1, and 1 minus 1 is 0. So 0, then 1 half, 2/3, 3/4, 4/5, and up to the n term, and so on. Another example is d sub n, where it is equal to negative 1 raised to n plus 1. This is actually an alternating sequence from 1 and negative 1. So we have 1, negative 1, 1, negative 1, up to the nth term, which is negative 1 raised to n plus 1, and so on. So convergence and divergence. Sometimes the sequence approaches a single value, or it means it converges to that single value as the index n increases. As an example, we have the sequence 1 over n. It approaches 0 as n increases. Since n is in the denominator, so each of the terms of the sequences gets smaller and smaller, and it approaches 0. Since as n approaches infinity, 1 over n approaches 0. So we can take the limit of 1 over n as n approaches to infinity. Another one is n minus 1 over n approaches 1 as n increases. By taking the theorems on limits, we can solve these things. On the other hand, sequences like square root of n approaches infinity as n increases, since square root of larger numbers is still large numbers, and so on. And another one is Negative 1 raised to n plus 1 never converges as it bounces back and forth between 1 and negative 1 as we have seen previously. So definition. So the sequence a sub n converges to the number L if for every positive number epsilon, there is an integer n such that for all n is greater than to that integer capital N, and it implies that the absolute distance between a sub n and L is less than epsilon. So as a graphical illustration, so as n increases, so for example, yung points na yan ay yung value niya ay a sub n. So yung height niya ay a sub n. So converges to L when yung n natin is mas malaki sa given larger n, where yung distance ng mga points mo from capital N is nasa loob lang ng interval na to. This is a distance of epsilon. Okay? Wala dyan hanggang dun. So, absolute distance. So, kung nasa taas o baba man, yung a sub n, nasa loob pa rin siya ng distance na epsilon away from L. So, that means, as n increases, hindi na siya lalabas dyan sa distance na yan. So, if there is no such L exists, we say that a sub n diverges. So, meaning kapag hindi ka nakakita ng number na unti-unting lumalapit yung value ng a sub n, nagda-diverge yung iyong sequence na a sub n. So, from the definition of limits, if a sub n converges to L, the limit of a sub n as n approaches infinity is equal to L. Or simply, the sequence a sub n approaches L, and L is the limit of the sequence. Definition, the sequence a sub n diverges to infinity if for every number large M, there is an integer large N such that for all n greater than large N, the value of the n term is greater than large M. If this condition holds, we write the limit of a sub n is equal to infinity as n approaches infinity, or a sub n approaches infinity. So as illustration, we have, so if the value of your terms gets larger than that as n increases larger than n, so that means the limit of your terms goes to positive infinity. That means hindi bababa yung value niya dun sa large M na yan. And similarly, if for every number smaller m, there is an integer large N, such that for all n greater than large N, if your value of each terms is less than small m, we say that a sub n diverges to negative infinity naman. Okay, so the limit of a sub n as n approaches infinity is equal to negative infinity, or a sub n approaches negative infinity. So if the values of your a sub n as n increases, mas mababa pa sa number m na yon, so the sequence approaches negative infinity. So pababa na pababa yung value ng a sub n. So theorems on limits of sequences. Let the limit a sub n as n approaches infinity is equal to a, and the limit of b sub n as n approaches infinity is equal to b. So sum rule, so just like in theorems of limits, the limit of the sum of the sequences as n approaches infinity is equal to the sum of the limits of the sequences. Difference rule, just like in sum rule, the limit of the difference is equal to the difference of the limits. Constant multiple rule, the limit of the product of a constant times a sequence is equal to the constant times the limit of the sequence. Product rule, limit of the product is equal to the product of the limits. Quotient rule, the limit of the quotient is equal to the quotient of the limits, as long as the limit of the denominator is not equal to 0. Examples. Limit of negative 1 over n as n approaches infinity is equal to, so we can factor out negative 1 as a constant multiple. So now we can take the limit of 1 over n as n approaches infinity. And the limit of this is 0. So negative 1 times 0 is equal to 0. Number 2, the limit of n minus 1 over n as n approaches infinity. So we can simplify the terms inside the limit. So we can have a binomial rather than a fraction. So 1 minus 1 over n. We can now use the difference rule. So the limit of 1 minus the limit of 1 over n. Limit of 1 as n approaches to infinity is still 1. Then the limit of 1 over n as n approaches infinity is 0. So we have 1. Number 3, limit of 5 over n squared as n approaches infinity. So we have 5 as a constant multiple times the limit of 1 over n squared. Since 1 over n squared is actually 1 over n times 1 over n, we can have a limit of the product. So 5 times the limit of 1 over n times the limit of 1 over n as n approaches infinity. So we have 5 times 0 times 0. So we have 0. And the limit of 4 minus 7n raised to 6 over n raised to 6 plus 3 as n approaches infinity. So simplifying or rationalizing rather, 4 over n raised to 6. So we divide all terms on both numerator and denominator by n raised to 6. 4 over n raised to 6 minus 7 over 1 plus 3 over n raised to 6. So taking the limit of both numerator and denominator, so since nasa denominator yung n ng 4 over n raised to 6, it approaches 0. Then constant yung 7. The denominator constant yung 1, so it's still 1, plus 3 over n raised to 6 as n approaches infinity, that approaches 0. So we have 0 minus 7 over 1 plus 0 is equal to negative 7 over 1, we have negative 7. Take note. So if the sequence made from the sum has a limit or sum converges, it does not tell whether each of the sequences a sub n and b sub n also have limits. So an example, so if a sub n is equal to 1, 2, 3, and so on, that sequence diverges since as n increases, same goes with the a sub n. And also b sub n is equal to negative 1, negative 2, and negative 3. It also diverges to negative infinity. But the sum of those sequences are all 0. So constant, the terms are all 0. It converges to 0. Meaning if the sum converges, it does not tell whether the sequences that you add are also convergent. So there's a sandwich theorem for sequences. Let a sub n, b sub n, and c sub n be sequences of real numbers. If a sub n is less than or equal to b sub n, which is less than or equal to c sub n, holds for all n beyond the index n, if the limit of a sub n is equal to the limit of c sub n as n approaches infinity and equal to L, then the limit of b sub n as n approaches infinity is equal to L also, since it is sandwiched between a sub n and c sub n. So one example, let's show that cosine n over n approaches 0. Since negative 1 over n is less than cosine n over n, less than or equal to positive 1 over n. Since cosine n, as n increases, so the values of cosine n only bounces back from negative 1 and positive 1. So cosine n over n is bounded between these two. So it is sandwiched between those two. And we know that since 1 over n approaches 0, so does negative 1 over n. And since na-sandwich yung cosine n over n sa gitna, by sandwich theorem for sequences, cosine n over n approaches 0 also. And 1 over 2 raised to n approaches 0 since 1 over 2 raised to n is sandwiched between 0 and 1 over n. So 0 approaches 0 and 1 over n approaches 0. So yung na-sandwich na sequence is also approaches to 0. Another is negative 1 raised to n times 1 over n since yung value ng 1 over n ay naglalaro lang sa negative and positive just like the example number 1. So negative 1 over n and positive 1 over n approaches 0. So same goes dun sa na-sandwich na sequence. So continuous function theorem. Let the sequence a sub n be a sequence of real numbers if a sub n approaches L and if f is a function that is continuous at L and defined at all a sub n, then f of a sub n approaches f of L. So let's show an example. Show that the square root of n plus 1 over n approaches 1. So using the continuous function theorem, so solution, since n plus 1 over n approaches 1, let's take f of x is equal to square root of x and L is equal to 1. So then f of a sub n approaches f of L, implies that your square root of n plus 1 over n approaches square root of 1, which is square root of 1 is equal to 1. So the square root of n plus 1 over n approaches 1. Another example, the sequence of 1 over n approaches 0 by taking a sub n is equal to 1 over n, then f of x is equal to 2 raised to x, and L is equal to 0. So we have 2 raised to 1 over n using the continuous function theorem. So f of 1 over n approaches f of L, and f of L is equal to 2 raised to 0, which is any number raised to 0 is equal to 1. So that means 2 raised to 1 over n approaches 1. So thus the sequence 2 raised to 1 over n converges to 1. So sample problem. So thus the sequence a sub n converges, whose nth term is a sub n is equal to n plus 1 over n minus 1 quantity raised to n. So nagko-converge ba yung sequence with that term? So finding the limit of a sub n as n approaches to infinity. So we have that. Now let's divide each terms of the numerator and denominator by n. So we have 1 plus 1 over n over 1 minus 1 over n, quantity raised to n. So for this, we have a limit of a power. By theorems on limit, this is the power of the limits. So we can take the limit of the inner function. So we have 1 plus 1 over n approaches to 0. Also this 1. So we have 1 over 1 raised to n, and as n approaches to infinity, we have 1 raised to infinity. This is actually an indeterminate form, so we can apply L'Hopital's rule by changing the limit into infinity times 0 by taking the natural logarithm of a sub n, since we have a limit of a power which became indeterminate form. Taking the natural logarithm of a sub n, we have ln of n plus 1 over n minus 1 raised to n. Simplifying that, so we can bring down the power as a factor, so n times the ln of n plus 1 over n minus 1. Taking the limit of both sides, we have limit of ln of a sub n is equal to the limit of n times ln of n plus 1 over n minus 1, which approaches infinity times 0, which is also an indeterminate form. So we can manipulate the function by putting the factor n into the denominator. So we have the limit of ln of n plus 1 over n minus 1 all over 1 over n. So now this is equal to 0 over 0. Now this is still indeterminate. Since now this is a quotient, we can use the L'Hopital's rule. So by taking the L'Hopital's rule, we have negative 2 over n squared
minus 1 all over negative 1 over n squared. So we take the derivative, both numerator and denominator, and then simplify it. This is now equal to the limit of 2n squared over n squared minus 1, since na-cancel out na natin yung negative, and we take the means and extremes. So this is equal to 2 by taking the limits. Since ln of a approaches 2 and f of x is equal to e raised to x, since ln of a sub n is approaches 2, since ln of a sub n approaches 2, and now we can see that the function f of x is actually equal to e raised to x is continuous. Since ln of a sub n approaches 2 and that the function f of x is equal to e raised to x is continuous, and we have the identity a sub n is equal to e raised to ln of a sub n. Now ln of a sub n approaches 2, so this one approaches e raised to 2. Thus the sequence a sub n converges to e raised to 2. So it converges. So these are the most commonly occurring limits. We have the limit of ln of n over n is equal to 0 as n approaches infinity. And the limit of nth root of the n is equal to 1 as n approaches infinity. Limit of x raised to 1 over n. As n approaches infinity, it is equal to 1, where the x is a positive number. Number 4, we have the limit of x raised to n is equal to 0 as n goes to infinity, where the absolute value of x is less than 1. Number 5, we have limit of 1 plus x over n quantity raised to n. As n approaches infinity, this is equal to e raised to x for all values of x. Number 6, we have the limit of x raised to n over n factorial. As n approaches infinity, this is equal to 0 for all values of x. Now we have the bounded monotonic sequences. So definition, we have a sequence a sub n is bounded from above if there exists a number big M such that a sub n is less than or equal to big M for all n. The number big M is an upper bound for the sequence a sub n. If big M is an upper bound for the sequence a sub n, but no number less than big M is an upper bound for the sequence, then big M is the least upper bound of the sequence. Also, we have a sequence a sub n is bounded from below if there exists a number small m such that a sub n or yung mga terms ng sequence natin is greater than or equal to m for all n. The number small m is the lower bound for the sequence. If small m is a lower bound for the sequence, but no number greater than m is lower bound for the sequence, then m is the greatest lower bound for the sequence. If the sequence a sub n is bounded from above and below, it is bounded. If the sequence is not bounded, we say that it is unbounded. Ito yung sinasabi doon. So bounded, not monotonic sequence. The sequence bounces between its bounds and fail to converge to any limiting value. So meron tayong bounds. So yung upper bound natin na m and the lower bound ni small m. So yung mga values ng sequences ay nandun lang sa loob and wala tayong pattern na papataas o pababa. So it does not converge to any limiting value. But in terms of a non-decreasing sequence, meaning yung values ng a sub n ay hindi bababa, it's either increases or be constant, have an upper bound m, then they have a limit L which is less than or equal to the value of the upper bound. Definition: the sequence a sub n is non-decreasing if a sub n is less than or equal to a sub n plus 1. meaning the next term can be equal or larger than the previous one. So non-decreasing. So it is either getting larger or constantly the same value. That is, the a sub 1 can be less than or equal to a sub 2, which is less than or equal to a sub 3, less than or equal, and so on and so forth. And the sequence is non-increasing if the previous term is larger or equal to the next term for all values of n. And the sequence said to be monotonic if it is either non-decreasing o kaya naman ay non-increasing. So either one of the two, monotonic yung non-decreasing at saka non-increasing. So theorem, monotonic sequence theorem. If a sequence a sub n is both bounded and monotonic, then the sequence converges. Bounded means there is a limit to the value, and monotonic, either non-decreasing or non-increasing, then the sequence converges. Now we have infinite series. So given a sequence of numbers a sub n, an expression of the form, so sum of the terms of the sequences, is what we call an infinite series. So series is the sum of the terms of a given sequence of numbers. So the number a sub n is the nth term of the series, and the sequence s sub n defined by s sub 1 is equal to a sub 1, s sub 2 is equal to a sub 1 plus a sub 2, up to s sub n is equal to a sub 1 plus a sub 2 plus and so on and so forth, a sub n, which is equal to the summation of a sub k, where k is from 1 up to n. So this is the sequence of partial sums of the series. So partial sums, so kung pang ilang n yung kinukuha natin, that is the number s sub n. It is the nth partial sum. So partial meaning part lamang ng infinite series. So if the sequence of partial sums converges to a limit L, so yung s sub n converges to a limit, we say that the series converges and that its sum is L. So kung nagko-converge yung partial sum into a specific number, that is its sum. So the infinite series is equal to the summation of the terms from 1 to infinity, which is equal to L, and that is the sum. If the sequence of partial sum of the series does not converge, we say that the series diverges. So kung wala ka makukuhang sum or a specific number na dun nagko-converge, so yung series is diverging. Number one example of infinite series are the geometric series. Geometric series has series in the form a plus a times r plus a r squared plus up to a r raised to n minus 1 plus so on and so forth. It is the summation of a r raised to n minus 1, where n is from 1 to infinity. Or it can be simplified as a summation of a times r raised to n, as n starting from 0 to infinity. So changing of index lang. In which a and r are fixed real numbers and your initial term a is not equal to 0. If r is equal to 1, so the partial sum is equal to a plus a times 1, which is yung r, plus a times 1 squared, plus and so on and so forth. So sinasubstitute lang natin yung r. So we have n terms of a. We have added a n times. So we have n times a. So the series diverges because the limit of the partial sum as n approaches infinity, since may factor tayo na n, as n approaches infinity, the limit of the partial sum is equal to positive or negative infinity depending on the sign of a. And if r is equal to negative 1 naman, so the series diverges because the nth partial sum alternate between a and 0. Because if this is negative 1, so a minus a, 0. Plus a, so we have a. Then the following terms will be alternating to the sum of a and 0. So it diverges. If r is not equal to 1, so we can determine the convergence and divergence by solving S sub n. So the partial sum is equal to a times 1 minus r raised to n over 1 minus r. So if the absolute value of r is less than 1, from negative 1 to positive 1, then r raised to n approaches 0 as n approaches to infinity. And yung partial sum would be approaching to a over 1 minus r. So you can see that the sum of the geometric series is equal to this formula. So it converges. If the absolute value of r is greater than or equal to 1, then the absolute value of r raised to n, doon sa formula natin dito, approaches to infinity. So the numerator approaches to infinity, the series diverges. So we only have a convergence if the absolute value of r is less than 1. Examples. So number 1, the geometric series with the initial term 1 over 9 and common ratio 1/3. So ang partial sum is approaching a over 1 minus r. So if this is our series, 1 over 9 plus 1 over 27 plus 1 over 81, this is actually equal to the summation of 1 over 9. So this is our a. Then 1 over 3 is r raised to n minus 1, as n is from 1 to infinity. So this is equal to the sum of 1 over 9, which is a, over 1 minus 1/3, so 1 minus r. This is equal to 1 over 6. So number 2, so the series given by the summation of negative 1 raised to n times 5 over 4 raised to n, where your n is from 0 to infinity, is equal to this. So our initial term is 5 minus 5 over 4, since we have an alternating series, then plus 5 over 16, then minus again 5 over 64. Now we can see in this pattern in the series, it is a geometric series with the initial term 5 and common ratio of negative 1/4. And it converges to a over 1 minus r, which is equal to 5 over 1 minus negative 1/4. So simplifying that, we have 5 over 1 plus 1/4, since negative times negative is positive. And this is equal to 5 over 4 plus 1 over 4, since 1 plus 1/4 is getting the GCD, which is equal to 4. Then we have 5 over 5/4, then multiplying by the reciprocal of the denominator, 5 times 4 over 5, cancelling 5, we have 4. So that is the sum of the series, and it converges to that sum. Another example, number 3, dropping a ball from a height of a meters, so variable yung height, a, above a flat surface, it rebounds a distance of r times the height, which is equal to r times a, where r is from 0 up to less than 1. So 0 is less than or equal to r, less than 1. Find the total distance traveled up and down if a is equal to 6 meters and r is equal to 2/3. So dropping a ball from height of a, so yung distance from the ground is a, so it bounces back and rebounded with the distance of a times r. So height times r. So given that r is 2/3 and the total height is 6 meters. Now, we're going to find the total distance traveled from this point hanggang tumigil siya sa flat surface, and finding the total distance nitong pag-bounce up and down niya. So paano natin makukuha yung distance niya? So as a solution, so the sum is, so given the initial drop a, plus 2 times yung pag-bounce niya AR, plus yung second bounce 2 times, because we have up and down. So the distance traveled up and down. So at this point, we have 2AR, then dito, 2 times AR squared, 2 times AR cubed, and so on. So we have a series of this one. So yung series with multiples of 2, it is a geometric series with A, which is 2AR, and the common ratio of R. So we have 2AR over 1 minus R. And simplifying this, we have GCD of 1 minus R, so A times 1 minus R, then plus 2AR. Then common factor of A, so matitira sa loob is 1 minus R plus 2R, then denominator of 1 minus R. So negative R plus 2R is positive R. Then substituting the values of A, we have 6, and yung R, we have 2/3, so 1 plus 2/3 over 1 minus 2/3. So we have 6 times 5 over 3 over 1 over 3. Now simplifying that, that is actually 30 meters. Expressing repeating decimals, 5.2323 and so on, has a ratio of 2 integers. So we can use the convergence of infinite geometric series for this. So as a solution, so we have the given decimal. So this is actually the sum of the 2 digits over its place values. We can show that 0.23 is equal to 23 over 100 plus 0.0023 is equal to 23 over 10,000, since it is in the 10,000s place, so and so forth. So we can see that in the patterns on the decimal part, we have a factor of 23 over 100 times a series with 1 plus 1 over 100 plus 1 over 100 squared. It is a geometric series with A is equal to 1 and R is equal to 1 over 100. So we have 5 plus 23 over 100 times yung sum ng geometric series, A is equal to 1 over 1 minus the R is 1 over 100. Simplifying that, we have 1 over 99 over 100. Then multiplying by 100, so we can cancel this out because multiply this, so cancel natin. So we have 23 over 99. It is equal to 495 plus 23 over 99, and in the end it is equal to 518 over 99. So the next topic are the tests for convergence and divergence. So geometric series is already discussed. Next is the n-term test. Next, p-series test, integral test, comparison test. So we have 10 sets of tests for convergence and divergence of series.